Split plot design has been widely used, particularly in agronomy research. In a split plot design, the experimental units are divided into smaller units. Split plot designs are useful when some factors are difficult or expensive to change, or when the levels of the factors cannot be fully randomized. A split plot design consists of one whole plot and one subplot. The whole plot factor is randomly assigned to the experimental units, while the subplot factor is applied to a smaller subset of the experimental units, usually nested within the whole plot factor. Today I'll explain the definition of split plot design and the corresponding statistical model. Here is an example dataset. This is grain yield data for 4 different genotypes subjected to 4 different treatments. There are 2 factors, genotypes and treatments, each with 4 replicates arranged as blocks. If you're a researcher, how would you set up the experimental design? The most common approach is a 2-way ANOVA with blocks. In this case, it is called the Randomized Complete Block Design, RCBD, and the experimental design would be structured as shown below. Although this is the most common way to set up an experimental design, it can pose some challenges when the number of treatments increases. As the number of treatments grows, it becomes difficult to maintain homogeneous conditions within a block. Additionally, issues arise when experimental factors have biological or physical constraints. For example, if CV1 involves virus inoculation, a completely randomized design could be problematic because the virus might spread to non-virus genotypes. Similarly, if a specific treatment involves planting date, it would be impractical to plant crops using a tractor at different times within a randomized design. To overcome such challenges, the split plot design is recommended. In the first example, if we set up genotype as the main plot and treatment as the subplot within each block, the experimental design would be structured as shown below. In a split plot design, compared to RCBD, the significance of the main plot effect is generally reduced, while the significance of the subplot effect is increased. Additionally, the significance of the interaction between the main plot and subplot is also enhanced. The key points are as follows. First, if a factor is considered more important for detecting significance, it is better to set it up as the subplot factor. Conversely, if the effect of a factor is already well understood, it should be designated as the main plot factor. Second, if the main effect of one factor is much larger than that of another factor, B, it is advisable to set factor A as the main plot. Third, in field experiments, when a factor is difficult to differentiate or manipulate easily, it is better to designate it as the main plot. For example, factors such as nitrogen amount and water amount are often set as main plot factors. If you run a statistical program as RCBD or split plot design, you'll obtain different ANOVA tables. The whole table for split plot design would be below. Let's compare the degree of freedom of RCBD with split plot design. What is different? In RCBD, the degree of freedom was 45, but in split plot design, it was split as error A, which is the error for the main plot, and error B, which is the error for the subplot. From now on, let's focus on the F ratio in each ANOVA table. The F ratio is the ratio between each mean square and mean square error, MSE. For example, the F ratio of genotype in RCBD is calculated as 949.3 divided by 30.0, which is approximately 31.65. How about the F ratio of genotype in split plot design? It was 949.3 divided by 68.70, which is approximately 13.81. The mean square is the same as 949.3, and only the MSE was changed. MSE is calculated as the sum of squares in residual divided by the degree of freedom in residual. In RCBD, MSE is 3049 divided by 45, which is approximately 30.0. However, in split plot design, MSE at the main plot is 618 divided by 9, which is approximately 68.7. Low F ratio indicates that the treatment effect, genotype, would be decreased or less significant. This is because when the variance of errors called MSE is increased, the genotypic effect becomes unclear. In split plot design, compared with RCBD, the significance of the main plot would be decreased, while the significance of the subplot would be increased. Also, the significance of interaction between main and subplot would be increased. This is why the significance of the main plot would be decreased, mainly due to increased variance of errors in the main plot. Now let's see the subplot. The F ratio of treatment in split plot design was increased to approximately 2.79, and the F ratio of interaction between treatment and genotype was also increased to approximately 3.20 compared to RCBD, where F ratios in treatment and interaction are 1.89 and 2.17, respectively. This is due to the decreased MSE in the subplot. The main benefit of split plot design is to split the variance of errors as error A and B, which increases the significance of the subplot and the interaction between main and subplot. Now let's practice setting up a statistical model using a statistical program. In most programs, it's quite straightforward to set up the statistical model for a split plot design. In the case of JMP, we need to set up the model step by step. Select Analyze and then Fit Model in the menu. In Y, select Yield, and in Construct Model Effects, first select Block, and then select Random Factor in Attributes. The whole model construction will be below. In the main plot, block and the interaction between genotype and block are random factors, and genotype is a fixed factor. In subplot, treatment and interaction between genotype and treatment are fixed factors. Let's select Method as EMS, Traditional. Now we can see the interaction between genotype and treatment. In split plot design, the significance of interaction between two factors would be more increased than in RCBD, and I told you this is because due to splitted errors, MSE in error B will be less than MSE in RCBD. For more information, please visit agronomyforfuture.com. Thanks.